Have you ever tried to mark a boundary on something that has no edge? Stand at the shore of night and ask, where does space stop at the edge of our atmosphere, the heliosphere, the Milky Way's halo, or the limits of what light can reach? Each answer sounds right, and each one moves the goalpost. We'll walk through those layers step by step, air to vacuum, solar wind to interstellar medium, galaxy to cosmic web, horizon to horizons. Along the way, we'll test what edge even means when geometry bends and expansion carries everything farther apart. If clear, careful exploration is your thing, a quiet, like, and subscribe helps others find it without breaking the flow. Settle in. By the end, the question may not vanish, but it will get sharper. The question of an edge sounds simple at first. Does space stop, or does it go on forever? The more we look, the more the word edge starts to bend. In daily life, an edge is a clear border, a fence line, a cliff, the rim of a cup. You can point to it and say, here it ends, and there it does not. Our minds like lines like that because they help us move through the world with confidence. We carry those habits into the sky and expect the same kind of boundary. But the universe does not act like a field with a fence or a page with a margin. When we try to press that picture onto the cosmos, it slips. Many early models of the heavens treated the sky as a roof or a shell. Stars were set on a sphere. The sphere kept everything tidy and closed. If you walked far enough, you would hit the outer layer, or so the story went. Modern physics replaced that shell with a different idea. Space is not a container holding things. It is part of the thing itself. Albert Einstein's general relativity says space and time form one fabric, called space-time. Matter and energy tell this fabric how to curve. The curved fabric tells matter how to move. Gravity is not a pull from a hidden rope. It is the path things take through curved space-time. That frame changes how we think about edges. If space is made of relationships, distances, and times between events, then a wall at the end of space is not a simple add-on. It is a claim about whether those relationships can even be defined beyond a certain limit. A simple picture helps. Picture a foggy field at night. You can only see a few steps ahead, but the ground keeps going. Your horizon is not the field's edge, it is the edge of your sight. The universe gives us a similar situation. We live inside the observable universe, the region from which light has had time to reach us since the start of cosmic history. Light moves very fast, about 300,000 kilometers per second, but not infinitely fast. The universe also has a finite age. Put those two facts together, and you get a limit. There are places whose light has not had enough time to get here yet. They may exist. We just cannot see them. This limit has a size we can state. If you take the age of the universe, about 13.8 billion years, you might guess the radius of what we can observe is 13.8 billion light years. That would be true in a static space. But space has been expanding while the light traveled. Distances stretched. The most distant galaxies we can see now sit about 46 billion light years away. That gives a sphere of visibility about 92 billion light years across. This sphere is not a shell around all that exists. It is a horizon. Like the sea horizon, it is a limit of view, not a physical border. Beyond it, more space and more galaxies can lie, but their signals have not arrived. This matters because drawings often show a bright bubble and then blankness. The blankness can look like nothingness. It is not. It is simply unobserved. The difference between unseen and absent is easy to skip past, yet it is central here. Our bubble is a record of what can have touched us with light or other signals by now. Other observers in other galaxies would have their own bubbles. Each bubble overlaps with others, and taken together they hint at a greater whole that no single observer can capture. Horizon is one kind of edge, based on time and signal travel. People also use edge to mean a boundary in space. The two ideas often get mixed. A boundary in space is like the shore of an island. Go past it and you are in something else, or in nothing at all. A boundary in time is like the first entry on a timeline. Before that mark, the record does not extend. The cosmos might have one kind of limit, both, or neither. It could be finite in age, yet unbounded in space, like the surface of a sphere, extended into 3 dimensions. No edge to run into, but a finite total size. In some models, it could be infinite in both. Each option comes with tests and consequences. General relativity gives us tools to frame those tests. We can measure how space is curved on large scales. If the average curvature is positive, like the surface of a sphere, space could be finite without edges. If it is flat or negative, it could be infinite. Measurements of the cosmic microwave background, the CMB, the faint afterglow from when the universe was only about 380,000 years old, show patterns in temperature and polarization. Those patterns act like rulers laid across the sky. So far, these rulers say the geometry is very close to flat across the part we can observe. Flat here means lines that start parallel stay parallel, and the simple rules of Euclidean geometry mostly hold. Very close means our tools cannot yet rule out a gentle curve with a very large radius. If the radius is huge, space could still be finite, but the curve would be too small to pick up across our limited view. Topology, the study of how spaces connect, adds another layer. A space can be finite without a boundary if it wraps around in certain ways. The surface of Earth is the easy case. You can keep walking east and never meet a wall, yet the area is finite. In 3 dimensions, there are many possible wraparound shapes. If our universe had one of those topologies on scales not much larger than our horizon, the sky might show repeated patterns. The same patch of early universe could appear in different directions, like seeing the same room reflected in facing mirrors. Astronomers have searched the CMB for matched circles and repeating features. So far, they have not found convincing pairs. That does not prove infinity. It sets limits on the size and kind of wraparound that could hide within our horizon. The observable universe is also a time machine. When we look far, we look back. A galaxy 10 billion light-years away is seen as it was 10 billion years ago, not as it is now. The nearest star beyond the Sun, Proxima Centauri, appears as it was about 4 years ago. The Sun itself shines with light that left its surface roughly 8 minutes earlier. Andromeda, the nearest large galaxy, reaches us as it was more than 2 million years ago. At the outer limit of view sits the CMB. Before that time, the universe was a hot, dense plasma of electrons and nuclei. Photons could not travel far without scattering. Space was foggy to light. When the universe cooled enough for electrons to settle into atoms, the fog cleared and light streamed out. We see that release today as microwave radiation, stretched by expansion. Other messengers help us probe past that foggy wall. Neutrinos, very light particles that rarely interact, decoupled earlier and could carry clues from a younger universe, though they are hard to detect. Gravitational waves, ripples in space-time, travel freely even through the early hot plasma, and future detectors may read signals from times where light is blind. Each messenger has its own horizon and its own reach. Expansion shapes another kind of horizon, the event horizon of our cosmic future. Dark energy, a form of energy built into space itself, causes the expansion to speed up. Galaxies that are far enough away will recede so quickly that new signals they send will never reach us, no matter how long we wait. We can still receive light already on the way, but fresh information will be cut off beyond a certain range. Picture a boat on a river moving away from you while the current grows stronger. For a time, you can still see new flags raised on the deck. Far enough out, the current sweeps the boat beyond the line where any new flag can ever catch up. This horizon is not a wall placed in space. It is a limit set by the global behavior of expansion. Thinking in terms of light cones makes these limits clear. A light cone is a diagram that sorts events by whether they can be linked by signals moving at or below the speed of light. Your past light cone contains all places and times that could have sent a signal to you by now. Your future light cone contains all places and times you can affect with any signal you send out. Outside those cones are regions forever disconnected from you, given the rules of the universe. Light cones are not objects you could bump into. They are maps of cause and effect. They remind us that distance alone does not decide what is reachable. Time and expansion matter just as much. Our habits still push us towards simple images, walls, shells, balloons, because they give form to the abstract. The balloon surface analogy has real value. As the balloon inflates, every point on the surface sees other points move away, and there is no special center on the surface itself. Yet even that picture misleads if we take it too literally. The balloon expands into a surrounding room. Our universe, in standard models, does not expand into a larger space. Distances between points grow. There is no need for an outside. The safest way to use analogies is to grab the one idea they carry well and let the rest go. All of this returns us to the human side of the question. It is natural to want an answer that settles the matter, finite or infinite, edge or no edge. What we can say with care is this: the observable universe is a sphere about 92 billion light-years across, centered on us. That sphere marks a horizon of visibility, not a physical border. Evidence so far suggests large-scale geometry is very close to flat within that sphere. We see no strong signs of a small wraparound topology. The universe beyond our horizon likely continues, though we do not yet know how far or in what global shape. Because expansion accelerates, some parts of today's visible universe will slip beyond the reach of new signals in the far future. The word edge must be used with those limits in mind. It also helps to keep space and time edges apart in our thoughts. The Big Bang is not an explosion from a center into empty space. It is the rapid expansion of space everywhere. Asking, what is outside the universe? Treats the universe as an object sitting in a larger container. In relativistic cosmology, the universe is the total set of events and their relations. Outside does not refer to a place we could point to. A better way to ask is, do the relations that define space and time continue beyond what we can observe? And do they extend without bound? That is a scientific question tied to measurements of curvature, expansion history, and early universe physics. Inflation, a proposed brief burst of very fast expansion in the first tiny fraction of a second, offers one path to answers. Many models of inflation predict a universe that is very large, close to flat, and smooth on big scales. Some versions even suggest space could be effectively infinite, with our observable patch just one region among many. Tests of inflation look for details in the CMB, such as specific patterns in polarization or subtle non-random features in the temperature map. So far, the data fits a simple, nearly scale-invariant pattern well. That keeps inflation on the table, but does not settle every detail, including global size. Dark energy is another active area. Its strength and behavior over time decide how horizons evolve. Observations of distant supernovae, the CMB, and the way galaxies cluster all point to a universe where dark energy acts much like a constant energy density in space. If that holds, the event horizon is a lasting feature. If dark energy changes in time, the future horizon might change too. These are questions where better measurements can sharpen the picture. From a practical view, the horizon we have is already large enough to fill a lifetime of study. Within it lie hundreds of billions of galaxies, each with billions of stars. Their light spans the electromagnetic spectrum, from radio to gamma rays. Gravitational waves from merging black holes and neutron stars pass through us. Neutrinos from distant explosions whisper by in tiny numbers. We use these signals to build models that bridge what we can see to what we cannot. Every new survey, every new detector, pushes the boundary of knowledge a little farther out. The idea of an edge does not vanish. It splits into types we can name. There is the edge of what we can see today. There is the edge of what we could ever influence. There is the edge in time, back to when light first moved freely, and earlier still, where only other messengers might speak. A global spatial edge may not exist at all. Each layer follows its own rules and allows its own tests. Sorting them keeps our words precise and our expectations clear. Now put that beside a simple trip in a straight line under a clear sky. If space is infinite, the path has no end. If space is finite yet unbounded, the path could bring you back to your start without ever meeting a wall. In both cases, the missing cliff is not a problem. It is how large-scale geometry works. With that in mind, edge shifts from a yes or no puzzle to measured questions we can check. We list what is observable, model how curvature or a wraparound would show up, and look for those patterns. Evidence arrives as small tilts in a graph or faint symmetries on a map. Bit by bit, the picture that fits the universe replaces the picture in our heads. Causality adds the cleanest edges. If a galaxy sits a billion light years away, we see it a billion years in the past. Newer events there are still in flight. Turn the view around, and you get your future light cone, the set of places and times your signals can reach, if nothing outruns light. Switch on a flashlight. The moving front of photons marks the growing limit of your influence. For the moment, it includes nearby buildings and trees. In years, nearby stars. Given millions of years, parts of the galaxy. This edge is not about walls or hope. It is a boundary drawn by physics, sharp, testable, and always tied to what can connect to what. Between the past and future cones sits the thin plane we call the present. Physicists often say, here and now. It is where the cones touch. Everything you measure and remember lies inside your past light cone. Everything you could ever affect lies inside your future light cone. This simple picture organizes cause and effect. It also brings us to causality, the rule that effects follow causes and that no usable information moves faster than light. Without causality, timelines would tangle, messages would arrive before they were sent, actions would be undone by their own results. The shape of the cones prevents this. If two events sit outside each other's light cones, neither can influence the other, no matter how strong the signal. The universe sorts interactions The way a calm traffic system sorts cars at an intersection. There are paths that can meet and paths that never will. This is not just abstract geometry. Consider two galaxies so far apart that space between them is growing faster than light could cross. Even if both send signals forever, new signals will never connect them. They are causally disconnected. Each keeps its own story. On smaller scales, the idea stays the same. Drop a pebble into a pond. Ripples spread in a circle, and only points inside the ring are affected. In space-time, the ring is a cone that grows with time. Anything outside the cone remains untouched. With this lens, the end of observation gains a clean meaning. We cannot see beyond our observable universe because the past light cone of our current moment does not reach farther. As time passes, the cone grows, and more of the universe may slip inside. Yet some regions will never enter because the expansion of space pulls them away too fast. Their light will never join our cone. The limit is not a wall. It is the geometry of light cones laid over an expanding metric. Think about a distant star whose photons have not yet reached Earth. Today, it sits outside our past light cone. In a million years, its first light may step in and become visible. Now think about other galaxies already so distant that the accelerating expansion driven by dark energy will keep every new signal from ever arriving. For those, the end of observation is permanent. This is a horizon written into the future shape of space-time. Where space stops is not about a cliff you could hit. It is about where signals can fit inside a cone drawn by the speed of light and the history of expansion. What lies beyond remains real, but is forever beyond contact. The cosmos is not denying access with a barrier. It is describing which connections are possible. Black holes fit into the same picture. The event horizon of a black hole is not a physical skin. It is the place where future light cones tilt so strongly inward that all possible future paths lead deeper in. Cross that surface, and every direction your future could take points toward the center. No rocket thrust can tip your cone outward again. The edge of a black hole is a change in the structure of cones, a reshaping of cause and effect. On the largest scales, the cosmic event horizon works the same way. It is the limit beyond which new signals can never reach us, no matter how long we wait. In both cases, the boundary is about light and time, not about walls. It is tempting to imagine a viewer outside space-time who can see everything at once, free of cones and horizons. That picture misleads, because light cones are not obstacles laid on top of reality. They are part of what we mean by reality. Remove them, and you remove the rules that make events line up in time. The cones may sound restrictive, yet they clarify our place. The universe may be infinite, but each observer's link to it is finite. We live inside a shifting bubble of connection. Outside that bubble, the universe continues without us. Inside it, we find every galaxy we can study, every star we can measure, and every trace of our own actions spreading outward. When people hear that the universe is expanding, they picture an explosion. Sparks fly from a center. Fragments race through empty space. It feels natural because we know firecrackers and breaking glass. Cosmic expansion is different. There is no center in space and no outer container. What grows is the scale of distances, the fabric that measures separation. The metric changes with time. Galaxies are mostly not shooting through a fixed void. On the largest scales, they sit fairly still in their local neighborhoods, while the distances between neighborhoods increase. A kitchen image helps if used with care. Think of raisin bread dough as it rises. As the dough expands, every raisin moves away from every other. The farther the raisin, The faster its distance grows because there is more dough between them. From any raisin's view, the pattern looks the same. That is close to what we measure in the sky. Now add the caveat that matters most. Bread rises inside a room, and air surrounds it. Space does not. There is no oven outside the universe. The dough is all there is. The expansion does not need an external space to expand into. It is a change in scale within space-time. Once you accept metric expansion, redshift becomes clear. Light is a wave. As it travels through expanding space, the peaks spread out. The wavelength stretches, and the color shifts toward red. It is not that galaxies rocket away like cars on a highway. The highway itself is getting longer between the towns, and the wave crests are pulled apart during the trip. The more distance the light has crossed, the more stretch it has. That is why redshift increases with distance. This also explains how some galaxies can appear to recede faster than light. Nothing is breaking the speed limit because nothing is moving through space faster than light. The space in between is growing so fast that no new signal can catch up. On small scales, gravity cancels expansion. Galaxies hold together. Stars orbit inside galaxies. Planets circle stars. Your chair is not sliding away from you. Atomic forces and gravity keep local systems bound. Expansion becomes visible only when you average over vast regions, millions of light years and beyond. The balloon surface is another useful picture with the same warning label. Draw dots on a balloon, inflate it, and each dot sees others move away. No dot is the center. The surface has no edge, yet it is finite. The trap is to imagine the balloon growing into the room. That outside space is only part of the analogy. In standard cosmology, there is no larger room. Distances grow without an external container. If you prefer tools instead of images, think of a rubber band ruler. Mark equal ticks, then stretch the band. The number of ticks between two objects grows, even if the objects stay put relative to the rubber. The ruler changed. In cosmology, the ruler is the metric. Its change drives the growth in distance. This view reframes many common questions. What is the universe expanding into? Becomes, how is the scale factor changing with time? The first assumes an outside. The second matches the physics we test. Curvature adds another layer. Spatial curvature is not about seeing a shape from the outside. It is about how distances and angles behave inside space. On a flat sheet, the angles of a triangle add to 180 degrees. On a sphere, they add to more than 180 degrees. On a saddle, they add to less. Positive curvature, sphere-like, can make space finite without edges. Negative curvature, saddle-like, makes space infinite and changes how lines spread. Exactly zero curvature is flat. Cosmologists use the terms closed, positive, open, negative, and flat, zero. Each case carries consequences. A closed universe could be finite, yet unbounded. Walk long enough, and you would in principle return to your starting point without ever hitting a wall. An open universe would be infinite and have geometry where parallel lines slowly drift apart. A flat universe is infinite too, with Euclidean rules holding on average. How do we tell which case we live in? We use the sky as a measuring tool. The cosmic microwave background, the afterglow from when the universe was about 380,000 years old, contains hot and cold patches with a typical size set by early sound waves in the plasma. The apparent size of those patches on the sky depends on curvature. Measure the pattern, and you can infer the geometry. Current results point to very small curvature, close to flat, across our observable region. Close to flat means we cannot rule out a slight positive or negative curve with a very large radius. If the radius of curvature is far larger than our horizon, we would not yet notice the bend. Topology, how space connects, matters too. Space can be finite without a boundary if it wraps in certain ways. The surface of Earth is the simple case in 2 dimensions. In 3 dimensions, there are many possible wraparound spaces. If the wraps were small enough, we might see repeating patterns in the CMB, like matched circles from the same region seen in different directions. Searchers have looked for these repeats and found no strong evidence so far. That sets limits. If space wraps, it likely does so on scales larger than the observable region, or in ways too subtle for current data. All these pieces fit one quiet picture. Light cones decide which events can connect. Metric expansion stretches both distances and wavelengths. Horizons appear because signals need time to travel, and because expansion can outrun them. Curvature and topology set the global shape and decide whether a finite space can still have no edge. These ideas sound distant, yet they touch everyday speech. When we say, "We can't see that far," we are drawing a cone. When we say, "A galaxy is redshifted," we are reading the metric's growth from the color. When we say there is no center, we are accepting the raisin-bread view from any raisin seat. 2 habits keep the picture clear. First, separate what exists from what can be observed. The observable universe is a sphere about 92 billion light-years across, centered on us. It marks visibility, not totality. Second, separate motion through space from the expansion of space. On small scales, planets, stars, even galaxy groups, ordinary motion rules. On the larger scales, the changing metric rules. With those habits, common puzzles ease. Superluminal recession speeds stop looking illegal because nothing is outrunning light through space. Space itself is growing. The missing cosmic center stops feeling strange because every galaxy sees others receding in the same way, and edge stops suggesting a wall and starts pointing to limits set by light and time. You can feel the structure with a simple scene. Stand in a dark field and switch on a lamp. The growing glow is your future light cone widening into the night. Turn the lamp off and look up. The faint starlight you catch is your past light cone sending history down to you. Put such a diagram at every event and you get the scaffolding of causality. Within that frame, galaxies form and merge. Black holes tip nearby cones inward. Dark energy stretches the gaps, and the speed of light keeps order not as an added barrier, but as the rule that makes a single, consistent story possible. Against that frame, geometry sets the stage for destiny. A flat universe sits between the 2 curved cases. In a flat geometry, Euclid's rules hold on every large scale we can test. Parallel lines stay parallel, triangle angles sum to 180 degrees, and space extends without bound, not because it opens into something else, but because a flat metric does not force closure. Through much of the 20th century, scientists argued over which global shape matches our sky. The choice matters, because shape links to evolution. In a closed model with positive curvature, gravity can slow the expansion, and without dark energy, could even reverse it into a big crunch. In an open or flat model, expansion can continue forever. The pace it keeps depends on dark energy. Geometry sets the stage. The universe's energy content writes the script. We cannot step outside the cosmos to check its outline, so we turn to the oldest light available, the cosmic microwave background, the faint afterglow from when the universe was about 380,000 years old. That light carries tiny temperature ripples, a pattern seeded by sound waves moving through the early hot plasma. The typical size of those ripples at the time they formed is known from physics. Their apparent size on the sky today depends on the geometry of space between then and now. If space has positive curvature, the same physical feature looks larger. With negative curvature, it looks smaller. In a flat space, it looks just right. Satellite maps from missions like WEMAP and Planck measured this pattern with great precision. The results point to near flatness. Within current uncertainties, the large-scale triangle sum behaves as 180 degrees. The error bars are small, but not zero, so a slight positive or negative curvature with an immense radius remains possible. Think of standing on a beach with a meter stick. Locally, the surface looks flat. Only across very long distances does the roundness of Earth reveal itself. The near-flat result raised a deep question. Why should the early universe be so finely balanced between open and closed that it ends up almost flat today? That flatness problem helped motivate inflation, a brief phase of very rapid expansion in the first fraction of a second. Inflation would stretch any initial curvature toward flatness, much as blowing up a balloon smooths a small patch. Data are consistent with this idea, though details of the mechanism remain under study. Whether inflation is the full story or only a part, the measured near flatness is a major clue to the first moments. Flatness changes what we can expect within our horizon. Across the region we can observe, space behaves as if it were infinite. There are no obvious signatures of a small, closed volume that loops back on itself at scales we can currently see. That does not rule out gentler curvature beyond our reach. The universe could be like an enormous sphere whose curvature radius is far beyond our observable size. To us, it would still look flat, just as the ground looks flat to someone walking a short distance across a field. Our daily intuition strains against these pictures because we visualize shapes by viewing them from outside. Cosmology asks us to use internal tests, how lines and angles behave, rather than external sightlines. This is where the idea of finite yet unbounded matters. It sounds like a contradiction until we separate area or volume from edges. The standard analogy is a globe. An ant crawling on the surface can walk in any direction without finding a border. The surface has a finite area, yet it has no edge within its own two dimensions. The key is that straight paths on the surface geodesics curve back because of the surface's intrinsic geometry. Carry that logic into 3 dimensions, and you get a closed universe without walls. In principle, a traveler moving along a straight geodesic could return to the starting point after an enormous journey, never crossing a boundary. No outside space is needed. The closure is a property of the space itself, not a sign of an external container. This view challenges habits built from books, boxes, and fences. Maps end at their borders. A globe does not. We also carry another trap: the belief that moving straight always takes us farther away. That holds on a flat plane, not on a sphere. On a sphere, straight eventually bends you home. In curved spaces, finite size does not require a stopping point. The cure for these traps is to work with internal rules, measure angles, track the behavior of parallel lines, follow geodesics, Let the geometry tell you what straight and far mean inside the space. Mathematics gives precise examples of finite, edgeless spaces in 3 dimensions. One family is the 3 torus. Start with a cube. Identify opposite faces, so that stepping through one wall brings you in through the opposite wall. Do the same for all 3 directions, and you get a space that loops without boundaries. It has a finite volume, yet every path continues. There are other compact topologies as well, including twisted variants that connect faces with flips or rotations. These are not fantasies. They are allowed by general relativity and can be made to fit the known expansion history and matter content. If our universe had such a topology with a small enough fundamental size, light could wrap around and give repeated views of the same structures. You could, in principle, see the same galaxy in multiple places on the sky, each at a different stage of its past, like echoes in different directions. Searches look for these signatures. In the cosmic microwave background, a wrapped space could produce matched circles where the same patch of the early universe appears twice with a predictable relationship. Astronomers also check galaxy surveys for repeating large-scale patterns that would be hard to explain otherwise. So far, no strong, repeated patterns have been confirmed. That pushes any non-trivial topology if it exists beyond our current horizon scale or into forms too subtle for current data. The absence of evidence here does not prove infinity. It sets limits on how small and how simple a wraparound can be and still escape detection. Flatness also ties to the fate of the universe only when we include the energy budget. In older models without dark energy, positive curvature favored a future collapse. Zero or negative curvature favored eternal expansion. With dark energy acting like a nearly constant energy density in space, even a slightly closed universe can expand forever. The critical factor becomes the balance among matter, radiation, and dark energy. Observations indicate dark energy dominates today, so the large-scale expansion accelerates. Under that rule, distant regions drift beyond our event horizon. New light they emit will never reach us. This is not a contradiction to flatness. It is a statement about dynamics layered on top of geometry. The phrase infinite space often raises new worries. Infinity feels uncomfortable because we cannot list or picture it. Yet, the relevant test is practical. Does geometry force a return, as on a sphere, or permit lines to extend without closure, as on a plane or a saddle? A flat or negatively curved space passes that test. Whether space is truly infinite or only too large for us to detect closure is a measurement question, not a philosophical one. We chip away at it with better maps of the CMB, deeper galaxy surveys, and improved measures of distance and expansion. Each improvement tightens the bounds. Topology reframes the same concerns in a different language. Geometry measures lengths and angles. Topology counts connections and holes. A coffee cup and a donut differ in curves and angles, but share one whole. A topologist groups them together. For the universe, topology asks whether space connects back on itself and along which directions. A 3 torus has 3 independent loops. A more complex compact space might have a different set of loops or twists. Each choice would leave subtle statistical fingerprints in the sky, from the alignment of temperature ripples to the distribution of large-scale structures. None of these tests demands an outside perspective. They use internal properties only. These ideas also help keep separate what expansion means. We are not watching galaxies fly through a static backdrop from a central blast. We are watching the scale of the backdrop change. With that in mind, redshift becomes a record of stretching, not a record of rockets. Superluminal recession speeds at great distances become natural, not illegal, because they reflect metric growth, not motion through space. Local structures stay bound because gravity and other forces beat the gentle pull of expansion on small scales. Your room, your town, your galaxy are not drifting apart from within. Only when we average over much larger scales does the growth show itself. A flat universe within our horizon lets us do clean calculations. Light travels on straight geodesics across cosmic distances. Standard rulers and candles' features of known physical size or luminosity can be used to trace geometry and expansion. The first acoustic peak in the CMB power spectrum serves as a ruler for curvature. Type Ia supernovae track expansion history. Baryon, acoustic oscillations leave a faint preferred scale in the galaxy distribution. Another ruler. Together, these tools cross-check one another. They are not perfect, but they give a coherent picture that points to near-flat geometry, an energy budget dominated by dark energy, and a topology that, if non-trivial, is larger than we can currently probe. If space were closed and small enough, we might one day notice repeated structures even without the CMB. In practice, cosmic expansion makes a full round trip of light unlikely within the age of the universe. If the closure scale is large, that does not weaken the concept. It simply says, our instruments and the universe's timeline set the limits of what can be confirmed. The important habit is to keep speaking in operational terms. What measurement would differ if space wrapped one way or another? What pattern would we see if curvature were positive versus negative? What does the data show? The deeper value of this approach is intellectual honesty. We name what we have measured, near-flat geometry across our observable region, no obvious repeats in the oldest light, and dynamics that push distant regions beyond lasting contact. We separate what follows from theory alone, such as the existence of compact, edgeless spaces, from what observations can already test. We keep both on the table and let new data decide. That is how a question about edges becomes a set of clear statements about geometry, topology, and expansion, all framed by signals we can receive and send. If space is flat and infinite, any line you choose keeps going, and there is always more ahead. If space is closed and finite, every line eventually loops back, and the word beyond does not apply within the space. If topology is non-trivial, a straight path can return without ever turning in the local sense. These are not poetic spins, but clean cases in the same framework. Current evidence points to near flatness with no small wraparounds inside our horizon. That leaves two broad pictures on the table: an infinite flat space or a finite space, whose curvature, radius, and any wrap scale are too large to detect so far. In both pictures, the same rules of light, distance, and causality explain why we never meet a wall. Those rules also let us read the sky with confidence. The oldest light sets a standard ruler. The way galaxies cluster checks that ruler at later times. Redshifts record how the metric has grown. Horizons mark what can be seen and what cannot. Curvature and topology finish the job by telling us whether straight paths, close, or run on forever. Put together, these pieces give a steady meaning to edge in relativity, not a cliff in space, but limits set by light and time. Now picture a universe that could loop on itself. No outside, only connections. When we look back toward the earliest times, we do not see a flash. We see a smooth, faint glow that fills the sky. This is the cosmic microwave background, the CMB. Afterglow of the Big Bang is common, but fog lifting is closer to what happened. In the first hundreds of thousands of years, matter and light formed a hot, dense plasma. Free electrons scattered photons so often that light could not travel far. The universe was bright and opaque. About 380,000 years after the start, cooling allowed electrons and protons to combine into neutral atoms. With far fewer free charges to scatter them, photons decoupled and began to move largely in straight lines. That release is called recombination. Those same photons have crossed space ever since, while expansion has stretched their wavelengths into the microwave band. The CMB is therefore the earliest light we can see. Not the first instant, but a backlit surface that records conditions when the fog cleared. That surface carries tiny temperature ripples, differences of only tens of microkelvin. Their sizes and patterns are the fingerprints of early physics. They anchor our standard ruler, constrain curvature, and set the initial seeds of structure that later grew into galaxies and clusters. Read correctly, the CMB ties together geometry, expansion, and causality in one sky-wide measurement, linking the question of edges to tests we can repeat and refine. What looks uniform at first is filled with tiny temperature differences, roughly a few parts in 100,000. Those small ripples carry a lot of information. They are the seeds from which gravity built galaxies, stars, and planets. Their pattern tells us about conditions in the young universe, average temperature, density, and the mix of matter and radiation. It even gives clues about geometry. If space were curved strongly one way or another, the apparent sizes of typical hot and cold spots in the CMB would shift. We can also use the CMB to test the idea that space might wrap back on itself. If the universe were finite and connected, light from the same patch of early plasma could reach us along different routes. On the sky that could show up as matched circles, pairs of circles on opposite sides with identical ripples. Finding such circles would be a clear sign of a finite, self-connected space. These are subtle tests. The CMB is faint, and the ripples are small. Space missions like COBE, WMAP, and Planck mapped the sky at microwave frequencies with high precision. Teams then searched those maps for repeating patterns. So far, no firm matched circles have been seen. The data fit either an infinite, nearly flat space, or a finite space so large that any repeats lie beyond our horizon. Even that absence helps. It means that if the universe closes on itself, its loop scale must be bigger than our current observable region. The CMB also supports the standard picture of cosmic history. It confirms that the universe once was hot and dense. It pins down the age at about 13.8 billion years. It shows that ordinary matter is only a small part of the whole. The rest is dark matter and dark energy, which we infer from how structures grow and how expansion changes. There is a quiet beauty in the CMB. You cannot see it with your eyes, yet those ancient photons bathe Earth day and night. Every direction you look holds a trace of the same early fog. The light does not illuminate the ground. It illuminates the shape of the universe. It is a map drawn in faint strokes, and we learn to read it by building instruments that can hear tiny differences in temperature and polarization. Whether or not we ever find repeated circles, the lesson stands. The biggest truths often come from the softest signals. To understand why the CMB looks so even and why space is so nearly flat, cosmologists proposed a brief period of very fast growth in the first fraction of a second, called inflation. For a tiny sliver of time, the scale of space increased at an extreme rate. This rapid expansion solved a puzzle called the horizon problem. Regions far apart in today's sky have almost the same temperature, even though, without inflation, they should never have had time to exchange heat. Inflation says they did share information because before the burst of growth, those regions were close together. The burst then pushed them far apart while keeping their temperatures nearly equal. Inflation also addressed the flatness problem. If space began with some curvature, the rapid stretch would make any bend look small within our observable patch, much like zooming in on a balloon makes a tiny area look flat. Inflation does more than smooth things out. It also provides seeds for structure. Quantum fluctuations, tiny, random jitters were stretched from microscopic scales to cosmic scales. These became small differences in density that gravity later amplified into the web of galaxies we see. The CMB's delicate pattern matches this idea well. The details still matter, and scientists keep testing them. Some versions predict a faint twist in the CMB's polarization made by ancient gravitational waves. Experiments hunt for that twist. A clear detection would strengthen the inflation picture and reveal the energy scale of those first moments. No single observation has sealed the case, but the broad fit between inflation and data is strong. Inflation tells us why our observable patch is smooth, large, and nearly flat. It does not by itself tell us whether the entire universe is infinite or only very big. That depends on how long inflation lasted and on details of the physics that drove it. If inflation ended quickly, space might be finite, but huge. If it ran longer, space could be so vast that it appears infinite to any observer within it. Some models say inflation never ends everywhere at once. Pockets stop inflating while others continue, producing many bubble regions with possibly different properties. That idea is called eternal inflation. It is an active area of theory, but direct tests are difficult. Our observations remain limited to the one bubble we live in, bounded by our horizon. The point is simple. Inflation shapes what we can measure, yet leaves the total size and global layout open. For much of the last century, the default view held that gravity should slow cosmic expansion. The big unknown was whether the slowdown would ever reverse into a collapse or simply flatten out toward a steady, slower growth. In the late 1990 seconds, two independent teams used Type Ia supernovae, exploding stars of nearly standard brightness, as distance markers. They found those supernovae were dimmer than expected, meaning farther away than models with steady or slowing expansion had predicted. The best explanation was that expansion is speeding up. A new component of the universe, later called dark energy, acts like an energy built into space itself. As space grows, there is more of it, and its push does not thin out in the same way matter does. The result is acceleration. Dark energy now makes up about 70% of the energy budget in the standard model of cosmology. It is not ordinary matter, not radiation, and not dark matter. The simplest version is a cosmological constant, a fixed energy density of empty space. In that case, acceleration continues indefinitely. Other ideas allow dark energy to change over time, but observations so far are consistent with a constant. Either way, an accelerating universe has a new kind of horizon. Today's observable horizon is set by how long light has had to reach us since the hot beginning. The future event horizon is set by acceleration. It marks a limit beyond which newly emitted signals will never catch up to us. Distant galaxies that are now visible will, in the far future, drift beyond that limit. Their fresh light will never arrive. This does not mean those galaxies vanish. It means our ability to exchange information with them ends. Over billions and trillions of years, more and more of the distant universe slips out of contact. Eventually, only galaxies bound together by gravity, our local group, remain mutually visible. The Milky Way and Andromeda are on a slow collision path and will merge into a large elliptical galaxy. That remnant and its smaller companions will hold together. Everything not bound will fade beyond reach. Future astronomers, born after that long fade, might see only a quiet island of stars and no sign of a broader expansion. The evidence we now use, the CMB, the relation between redshift and distance, the pattern of galaxies on enormous scales, would be gone to them. The sky would tell a smaller story even though the universe beyond still exists. The idea of a future horizon pairs cleanly with light cones. Your past light cone decides what you can see now. Your future light cone decides what you can ever influence. Acceleration pushes parts of today's sky outside your future light cone. No new signal from you can reach those regions, and no new signal from them can reach you. Black holes teach the same lesson in a stronger form. Near a black hole, light cones tilt inward, cross the event horizon, and your future paths all lead toward the center. The horizon is not a material shell. It is a reshaping of which events can still connect. The cosmic event horizon works the same way, but on the largest scales. It is a limit set by expansion, not by walls. Seen together, these tools, CMB maps, inflation, dark energy, and light cones, give a steady picture. The CMB shows us the first clear surface and provides rulers for curvature and distance. Inflation explains why the surface looks so smooth and why the geometry is close to flat, and it supplies seeds for structure. Dark energy explains why expansion speeds up today and why a future horizon exists. Light cones and horizons tell us which parts of the universe can ever be in contact. None of these ideas rely on stepping outside the universe. They use internal measurements, patterns on the sky, brightness and redshift of standard candles, and the way structures cluster. This picture also clarifies common misunderstandings. The Big Bang was not an explosion from a center into empty space. It was rapid expansion everywhere at once, with no special center. Redshift is not a Doppler siren from galaxies racing through a fixed void. It is a record of wavelengths stretched by expanding space. Faster than light recession at great distances is not a violation of physics. It is a feature of metric growth. Edge does not mean a cliff where things stop. It means a boundary of connection set by time and expansion. Outside does not refer to a place beyond space. It is a word that loses meaning when space is the whole stage. Topology adds one more layer. Geometry tells us about curvature, positive, negative, or zero. Topology tells us about how space connects, whether it loops and along which directions. A 3 torus, for example, is a finite volume with no edges. Step through one side, and you re-enter from the opposite side. If the universe had such a shape on scales not much bigger than our horizon, we might see repeated patterns in the CMB or in galaxy maps. We have looked and not found simple repeats, which pushes any RAP scale outward. Still, topology remains open. Space could be simple and infinite, or finite and cleverly connected, with loops far beyond what we can check today. None of this requires heavy math to appreciate. The key rules fit in a few plain sentences. Light has a finite speed. The universe has a finite age. Space expands, and the rate of expansion changes with the contents of the universe. Gravity curves space-time, and the pattern of that curve shows up in how light and matter move. From these rules, horizons arise. From these rules, we define what near and far mean on cosmic scales. From these rules, we understand why we can map the early universe at all, and why some answers must wait. The CMB remains our clearest guide. It tells us that the early universe was smooth, but not perfect, hot, but cooling, and nearly flat. It tells us that structure grew from small seeds into the cosmic web. It tells us that distance and geometry can be measured from patterns in ancient light. It does not answer every question. It cannot show us past recombination with photons, and it cannot tell us directly whether space closes beyond our view. But it sets strong boundaries and points to what to test next. Inflation adds an organizing idea. A brief, intense burst of growth can turn rough beginnings into a large, smooth, nearly flat patch, while stretching tiny fluctuations into the seeds of later structure. Dark energy adds a sober limit. Accelerated expansion means the future sky will thin, not because things end, but because contact ends. Light cones and horizons turn both stories into clear diagrams, sorting what can touch what now and ever. Taken together, they support one message. Space may be finite or infinite, simply connected or subtly looped, but there is no outer wall to find and no center to aim for. There is a past surface we can read, a present bubble we can observe, and a future boundary we cannot cross. The rest lies beyond the reach of our lantern. Under the stars, you are bathed in ancient microwaves, released when the first atoms formed. You also watch expansion lengthen the space between galaxies and stretch their light on its way to you. You live inside a pair of light cones that define what has reached you and what you can reach. The universe you share has its largest features written in tiny ripples and quiet accelerations. On paper, we draw spheres, saddles, planes, and loops to make sense of it. In practice, we measure microkelvin temperature ripples, small redshifts, and distances in light years. Those numbers turn shapes into tests. Piece by piece, the tests narrow the options. Piece by piece, the sky answers not where space stops, but how connection works across it. In this frame, an ending is a limit on communication, not on existence. Expansion continues. New space appears. Distant regions follow their own histories. What changes is access. Our chapter drifts out of contact with others, like a sealed book carried by a slow current. The edge question becomes a connection question. From one angle, space never stops. The scale factor grows, and the web keeps stretching. From another, our accessible universe shrinks in practice because fewer galaxies remain inside our future light cone. The end sits at the edge of contact, not at the edge of space. Black holes show the same logic in a sharper form. An event horizon is not where space-time ends, but the boundary beyond which no signal returns. A cosmic event horizon plays that role on the largest scale. Galaxies do not cease. Their messages do. This can feel a little sad, but it also locates our era. We live when the sky still carries the wider pattern clusters, filaments, and the faint glow of the oldest light. We can read the early temperature ripples, count distant supernovae, and trace the cosmic web. In the far future, much of that evidence will fade below detectability. The lesson is simple and steady. Our limit is a horizon, not a wall. What leaves our communicable future has not been erased. It has slipped past a boundary set by expansion and light speed. Expanding into what is the question that returns in every classroom and late-night talk. The image of a balloon in a room is strong because it matches daily life. A balloon needs air around it. A firework needs space to fly into. The universe does not. What grows is the metric, the ruler that defines distances. Galaxies separate because the ruler's tick marks stretch. There is no external warehouse of emptiness to occupy. The surface of a balloon analogy helps if we keep it honest. Draw dots on the surface and inflate it. Each dot sees others receding, and there is no edge on the surface itself. The trap is to smuggle in the room and the air. Those are features of the picture, not of reality. The same goes for curved grid diagrams that look like trampolines. They teach a single point that mass curves space-time, or that distances change, but the embedding space is not part of the physics. Space-time stands on its own. Our habits make this hard. We stack containers inside containers, cup on table, table in room, room in building, building on street. We then try to place the universe inside something larger. That move breaks the terms. Outside the universe has no coordinates because all coordinates live within space-time. Position is defined by the geometry we are discussing. Beyond it, the word where has nothing to attach to. Turning the question helps. Ask how the distance between far-flung galaxies changes with time. That is expansion. Ask how light's wavelength changes as it travels. That is redshift. No outside is needed to define either. Speculative ideas, like eternal inflation or multiverse pictures, sometimes imagine many bubbles. Those are interesting models, but they are not required to explain the observed expansion. The standard account, general relativity plus measured contents, already gives a universe that expands without an external stage. Bread dough with raisins guides the language well. You do not ask what the bread expands into to explain why raisins drift apart. The rising is intrinsic. In a closed finite space, a traveler could circle forever and return home without meeting a rim. In an open or flat space, the traveler could go on without looping and still never find a border. In any case, expansion stretches distances within the fabric itself. Peace comes from accepting the strangeness. Space is not an object inside a room. It is the framework that makes rooms meaningful. Asking what it expands into is like asking what time flows through. Time is the flow. Space is the growth. For most of our history, the cosmos was pictured as a stage under a dome or inside a shell. Relativity replaced the stage with a fabric that can be complete on its own, finite or infinite, without a larger container. Balloon cartoons and warping grids are just teaching aids. They work as long as we do not mistake the aid for the thing described. The clean answer to into what is into nothing at all. Not because there is a special nothing out there, but because into smuggles in an outside that the model does not have. This also changes what we mean by boundary. In ordinary life, a boundary is something you can touch. In relativity, Boundaries are often about information. Space-time is modeled as a smooth manifold, and matter and energy curve it. Within that setup, different edges can appear. Some are horizons limits, on which signals can get where. Others are singularities, places where the equations fail, signaling a true end to the description. The event horizon of a black hole is the familiar one-way curtain. Nothing in the math forces a bump when you cross. Locally, you feel normal gravity. The boundary shows up when you try to send a signal out. Future-directed paths do not escape. That is a limit on communication, not a physical shell. Be careful with map tricks too. A horizon looks like a blow-up in certain coordinates. In Schwarzschild coordinates, the metric components diverge at the horizon, as if something has become infinite. Change to coordinates that follow in falling observers, and the divergence vanishes. The horizon was smooth all along. What looked like an edge was a bad choice of map, like a Mercator projection, stretching Greenland to absurd size. The true singularity lies at the center, where curvature and density grow without bound in the classical theory. That is a different kind of edge. The manifold cannot be continued in any smooth way. Physicists distinguish these carefully. A coordinate singularity is a feature of description. A curvature singularity is a breakdown of the theory's predictions. The cosmological horizon offers the same lesson at cosmic scale. Today's observable limit, roughly 46 billion light-years away in co-moving distance, is not a border in space. Galaxies do not bounce there. In co-moving coordinates, ones that expand with the universe, galaxies sit at fixed positions while the scale factor grows. The horizon is the set of locations from which light has not had time to reach us. Nothing special happens to the galaxies that sit beyond it. The boundary lives in our causal diagram, not as a ring around them. It is the difference between not here yet and not there. Walls in daily life separate what exists from what does not. In relativity, many edges separate what can be described or contacted from what cannot. A region may exist and still be outside our past or future light cone. A formula may fail and still be replaced by a better one in a deeper theory. That is why labeling an edge demands care. We ask whether space-time can be extended smoothly beyond a suspected boundary. If yes, the edge was only in our coordinates. If no, we have hit a true end to the classical description. Even the strongest classical edges may not be final in nature. Singularities, places where classical curvature becomes infinite, likely mark the limits of general relativity, not literal infinities in the world. A quantum theory of gravity is expected to change the story near those extremes, replacing the blow-up with well-defined behavior. We do not yet have a complete, tested theory for that regime. The expectation stands because infinities in physics almost always signal the need for new rules. When those rules arrive, some hard edges may soften. This framework clarifies illusions created by language. Boundary of the universe invites a picture of a glowing bubble in a larger dark. The modern picture has different edges, horizons set by cause and effect, coordinate artifacts that vanish on better maps, and possible singularities where current equations break. None are fences in space. They are limits in the fabric itself. The observable universe is bounded by light travel time. Black holes are bounded by escape possibilities. The edges we keep track of are limits of influence, not slabs of matter. Turn back to dark energy with this in mind. Acceleration introduces a future event horizon, a sphere beyond which newly emitted signals will never reach us. It is not a wall that galaxies strike. It is a boundary in our causal future. Over vast times, more and more of today's galaxies cross that line. Their new light will never arrive, even though their old light still does, and their local physics goes on. Our observable past light cone continues to gather ancient signals from within the current horizon. Our future light cone shrinks in practical reach as acceleration carries would-be partners away. Both statements can be true because they refer to different cones, what can reach us and what we can reach. This double view also answers a quiet worry. If our accessible world shrinks in practice, does space end for us? No. The manifold persists. The metric keeps evolving. The boundary is about contact, not about being. Regions beyond still exist and interact with themselves. Their histories are simply decoupled from ours. The universe has not closed. Our chapter has. We can name that curve without turning it into a cliff. Teaching diagrams make all of this easier to hold. Use the balloon, but remember there is no room. Use the rubber band ruler, but remember the band is the distance scale, not a thing stretched on pegs. Use light cones and keep them front and center. They tell you what can connect. Use moving coordinates when you want to see galaxies at rest with respect to expansion, and proper distances when you want to see how intervals change with time. Switch maps when a map invents a problem. Do not let a coordinate choice pretend to be physics. From here, the catalogue of boundaries fits on a single page. There are horizons, which are limits of causal connection. There are coordinate singularities, which are artifacts of description. There are curvature singularities, which are likely signals that new physics is needed. There are no rims in space where matter piles up to form a cosmic fence. There are no outside rooms that the universe grows into in the standard picture. There are, however, operational edges everywhere. How far we can see, how far we can send, how deep our current theory reaches. Each has units we can measure. Each has tests we can improve. This way of thinking does more than fix language. It guides practice. When we ask, where does space stop? We write down what can be observed today, what can be observed in principle given enough time, and what can never be observed because of horizons that acceleration makes permanent. We check the CMB for curvature and topology. We measure redshifts and distances to track the growth of the metric. We search for gravitational waves from the earliest times to probe past the photon fog. We compare maps in different coordinates to strip away artifacts. We keep singularities in view as targets for quantum gravity, not as places to declare the world ended. Hold two pictures at once. The universe, seen as space-time, has no outer wall. It grows by changing its own scale. Within that growth, every observer carries a moving window set by light cones and horizons. Those windows define ends that matter to us, ends of sight and ends of contact. They are quiet, mathematical, and real. They do not stop galaxies from existing. They stop messages from arriving. That is the kind of edge we meet in cosmology, and the kind that explains why our sky looks the way it does. Learning to tell real limits from map tricks is a quiet triumph of relativity. It stops us from mistaking the habits of our language for the rules of the world. When you hear about the edge of the universe, think in terms of horizons and limits of description, not walls or cliffs. Space and time do not need material fences to be complete. Their boundaries are drawn in causality. What can connect, what cannot, and where our math stops being reliable. A universe can have edges that are not edges, boundaries that do not block, and horizons that describe the scope of knowledge rather than an ending of being. The Big Bang is a prime example of how language can lead us astray. The usual image is a firework, one bright point, blasting into an empty night. That is not what happened. The Big Bang was not an explosion in space. It was an expansion of space. There was no single center, no outer void that got filled. Every place we see today was once part of that hot, dense state. To picture it, use the surface of a balloon idea carefully. As the balloon inflates, every point on the surface moves away from every other. The expansion does not come from a special spot. The whole surface grows together. Our universe behaves like that in 3 dimensions. Space itself stretches, and matter rides along. Follow the equations of general relativity backward in time, and the density and curvature rise without bound. Pushed all the way, the math points to a singularity, a place where it breaks and gives infinite answers. At first glance, that looks like a sharp beginning, a literal first instant at infinite temperature and density. But singularities are warnings, not photographs. In physics, infinities usually mean the theory has been taken past its safe range. Newton's laws fail near light speed. Relativity may fail at the ultra-early, ultra-dense stage, where quantum effects dominate. Instead of a single point of creation, what we likely have is past incompleteness. Our current model cannot be extended further into the past. Something set up the hot Big Bang, but our tools cannot yet describe that before. This reframes the beginning. The Big Bang becomes a boundary in time for our equations, not a cliff in space. Think again about the balloon. Rewinding the film, the whole surface shrinks. The beginning is not a dot on the surface. It is the fading of the surface itself to 0 size. In the same way, the Big Bang was not a place in the universe. It was a state of the entire universe. To ask where it happened is to miss the point. It happened everywhere, because everywhere was once contained in that hot, dense state. This distinction helps with a common misunderstanding. If the Big Bang were a blast into emptiness, we could find a center. We cannot. No matter where an observer stands, tracing the view backward leads to the same hot, early state. There is no special vantage point. That may feel unsettling because we like centers and borders. Yet it is also precise. It says the origin is shared by all regions, woven into every particle and photon, not owned by a single corner of space. Whether time itself began at the Big Bang, or whether something existed earlier is open. If time began, then before is like north of the North Pole, not a valid direction. If the Big Bang marks only the limit of relativity, then there could be a prior phase, a quantum foam, a bounce from a contracting era, a larger inflationary landscape, where our region was one bubble among many. None of these possibilities has clear proof today. They are ideas under test. The honest statement is that the Big Bang marks where our present theory runs out. It is a page edge for our math, not necessarily for reality. Even if the Big Bang were an absolute beginning, it still would not mark a spatial border. It would mark a time boundary. The scale factor, the number that tells us the size of distances, would go to 0. Space as we know it would not exist before in any usual sense. That is a hard shift in viewpoint, but it clears away an old picture that was never quite right. A small spark expanding into a waiting room. There is no room. There is only the fabric itself, growing. Black holes carry the same lesson about edges. A black hole does not have a crust or fiery skin. Its defining feature is the event horizon, which is a rule, not a thing. Cross it, and no light can get out. Stand far away and you see a dark sphere. Fall in, and you feel no bump at the horizon, no sudden shock. Locally, physics looks normal. The change is global. Outside observers can no longer receive your signals. The horizon is a one-way curtain drawn by space-time itself. It marks where escape paths end, not where space ends. This curtain echoes the cosmic horizon of an accelerating universe. In a universe with dark energy, expansion speeds up. Past a certain distance, new signals emitted today will never reach us. That future event horizon is not a wall in space. Galaxies that cross it do not explode or bounce. They keep evolving on their own paths. The horizon marks the limit of future contact. Both black hole and cosmic horizons are boundaries of information, built from light paths and causality. The differences matter too. A black hole's horizon size depends on mass and sits around a central singularity in the classical theory. A cosmic horizon follows the expansion history and can grow or stabilize depending on dark energy's behavior. Inside a black hole, the rules for paths tighten. Every route leads inward, toward a singularity in the classical picture. That singularity likely signals where general relativity breaks and quantum gravity must take over. Outside, the black hole is oddly simple. From far away, you can describe it with only 3 numbers: mass, electric charge, and spin. This no-hair simplicity hides all other details. The horizon keeps the fine-grained story out of sight. The object becomes featureless to the outside, even though its interior is the most extreme stage we know. Horizons also carry temperature in quantum theory. Black holes glow faintly through Hawking radiation, losing mass over unimaginable times. A universe dominated by dark energy, well described by De Sitter Space, has a cosmic horizon with a tiny temperature too. The numbers are far beyond reach for direct detection now, but the principle is important. It says, horizons are physical. They are not only lines on a diagram. They have entropy and temperature, and obey thermodynamic-like relations that link gravity, quantum theory, and information. That brings us to De Sitter Space, a simple model of a universe with only dark energy. Remove matter and radiation. Leave a constant energy density in space. The result is smooth, exponential expansion. The scale of the universe doubles again and again at a steady rate, like compounding interest. Each observer finds a personal horizon, a finite bubble of visibility within an endless whole. Light from beyond that horizon will never arrive. The picture is calm. No lumps, no mergers, no shocks. The expansion smooths away irregularities and the large-scale view becomes unchanging. Physicists often call this a kind of attractor state. As matter thins out, the universe's behavior approaches this simple form. De Sitter Space reframes infinity. The universe can be endless, yet each observer's accessible region is finite. That is not a contradiction. It is a statement about causality. Your horizon sets your bubble of experience. Someone far away has their own bubble. Neither can see the other's sky. Knowledge is local. No single observer can claim the whole, not because the universe ends, but because the rules of light and expansion limit what any one vantage point can include. This dual view, endless whole, finite window fits the broader message of relativity. We do not search for walls. We map horizons. We do not demand a center. We track how distances change. We do not treat singularities as literal infinities. We treat them as places where our equations signal their own limit, and we watch for coordinate traps. In some coordinate systems, a horizon looks like a blow-up. In better coordinates, it is smooth. Like a bad world map that stretches the poles, a bad space-time map can invent edges. The cure is to check whether the geometry can be extended smoothly. If yes, the edge was an artifact. If no, we have found a true boundary of the classical description. With that mindset, the standard teaching tools fall into place. Use the balloon, but leave out the room. The balloon's outside belongs to the drawing, not to space. Use the rubber band ruler to explain metric expansion. The ticks stretch, so the number of ticks between 2 points grows, even if the points stay put relative to the band. Use light cones to sort what can touch what. The past light cone defines what we can see now. The future light cone defines what we can ever influence. Use moving coordinates to view galaxies at rest with the expansion. Use proper distance to see how far they are right now. Switch maps and check that physics, not coordinates, decides the answers. This perspective also clarifies everyday questions. Into what is the universe expanding? Into nothing, because into assumes an outside the model does not have. Expansion is a change in the metric. Distances increase. Where did the Big Bang happen? Everywhere, because every point was once part of the hot state. Where does the universe end? Where connection ends at horizons set by time, light, speed, and expansion, not where matter meets a wall. Why do some galaxies appear to recede faster than light? Because at great distances, the metric's growth can increase separation faster than light can bridge it. No law is broken, since nothing outruns light locally. Through space, the space between grows. Now return to the earliest evidence. The cosmic microwave background is our oldest light. It shows an almost uniform sky with tiny temperature ripples. Those ripples match the seeds predicted by inflation. Small quantum fluctuations stretch to large scales. Their sizes on the sky serve as rulers for geometry. They tell us that our observable region is close to flat. They also let us hunt for topology. If space wraps around on scales not much bigger than our horizon, we would expect repeated features matched circles in the CMB. We have looked with high-precision maps and found no convincing repeats. That does not prove infinity. It pushes any wrap scale farther out or into forms too subtle for current instruments. Inflation, as a brief burst of rapid growth, explains why the CMB is so even and why geometry looks so close to flat. It also makes our patch large enough to hold the structures we see today. But inflation does not force an infinite universe. Its total reach depends on how long it lasted and on the physics that drove it. Some versions suggest eternal inflation, where pockets finish inflating at different times, creating many regions with potentially different properties. That idea is bold and hard to test. The safe claim is narrower. Inflation, in some form, fits much of the data we have about the early universe, while leaving the global size an open question. Dark energy shapes the far future. It accelerates expansion and creates a future event horizon. Over long times, more and more distant galaxies cross that line. Their new light will never reach us. What remains visible are the galaxies bound to us by gravity, the local group which will merge into a larger object. Far beyond, the CMB will redshift to such long wavelengths that it becomes undetectable. Future astronomers born in that era would see a quieter sky. The large-scale story we read today would be hidden by horizons, not erased from reality, but removed from contact. De Sitter space is a clean sketch of that end-state behavior. It has a constant acceleration and a fixed horizon for each observer. It assigns a tiny temperature and a huge entropy to that horizon, hinting at deep links between gravity, thermodynamics, and quantum mechanics. It reminds us that even empty space is not empty in a naive sense. It comes with structure, with rules, and with subtle quantum effects. The calm is real, but it has a hum. The thread tying these topics together is simple enough to state. Light has a finite speed. The universe has a finite age. Space-time is dynamic. It can expand and curve. Horizons are the natural result. They define what can be known and shared. Singularities, when they appear in our math, are flags that we need a better theory in extreme regimes. Coordinates can mislead. Physics cannot. From these points, edge turns into a set of measurable limits, not a cliff. If we keep that thread in hand, we can read the sky with steady confidence. The CMB fixes rulers and clocks. Galaxy surveys trace structure and growth. Supernovae measure distance versus redshift and reveal acceleration. Gravitational wave detectors open new windows into violent events and, one day, maybe the very early universe. Each tool marks a boundary of what we can reach and suggests how to push it outward. None promises a final wall. All of them describe horizons past, present, and future that sought connection from silence. So the difference we learn to draw between walls and horizons, between coordinate artifacts and real limits, between the breakdown of a theory and the breakdown of nature, is more than a tidy bit of vocabulary. It is the backbone of modern cosmology. It keeps our questions sharp and our answers modest. It tells us that the universe does not stop. Our contact does. It tells us that the Big Bang is not a place. It is a time boundary for our current math. It tells us that black holes do not have skins. They have rules that shape which signals can escape. It tells us that an accelerating universe does not end in a fence. It ends in a horizon of farewell. These statements do not make the cosmos smaller. They make it precise. Infinity becomes personal when it is divided by horizons. The universe can be endless, yet each observer sees only a finite share, a private bubble marked by what light can reach and what signals can leave. Studying de Sitter space, the simple case where dark energy rules everything, helps us think clearly about our own accelerating cosmos. Observations show dark energy already dominates the expansion. As matter and radiation thin out, the large-scale behavior grows more de Sitter-like. Whether that calm lasts forever or gives way to new physics is unknown. For now, de Sitter space offers a clean balance. Finite horizons inside an unbounded whole. Steady growth paired with hidden regions. It teaches that no edges does not mean no limits. And a smooth sky does not mean a simple story. A universe can be infinite yet veiled, orderly yet puzzling, quiet and still deeply strange. Over time, many galaxies now visible will slide beyond our future event horizon until only the local group remains. The night will look emptier, but the universe will not have ended. It will look more like de Sitter space, serene, expansive, and filled with parts we can never contact. The end of contact is not the end of existence. Hidden regions persist, sealed away by the steady pull of accelerated expansion. Infinity and limits can live side by side. To study limits precisely, physicists use conformal or Penrose diagrams. These pictures look spare diamonds, triangles, straight lines at clean angles, but they pack a whole space-time into a small, readable map. The trick is to throw away absolute sizes while keeping angles. In these diagrams, light always moves at 45 degrees. That single rule makes causality, the order of influence, easy to see. You can trace which events can talk to which, where horizons form, and where paths must end. Start with flat, non-expanding Minkowski space. Its conformal diagram is a diamond. The bottom tip stands for past infinity, the top for future infinity, and the sides for spatial infinity. Light runs along the diagonals, so a glance tells you which signals can arrive and which cannot. Infinity is not pushed off the page. It becomes labeled edges within the picture. The diagram compresses the unbounded into a bounded sketch without losing the structure of cause and effect. Curvature adds interest without breaking the method. For a black hole, the event horizon appears as a clean boundary line, separating outside from inside. The diagram shows, in one stroke, that any world line crossing the horizon ends at the singularity in the classical theory. For an expanding universe, the diagram shows a cosmic horizon, a limit beyond which signals cannot reach us. In both cases, the edge is causal, not material. You can pass a horizon without bumping a wall. What changes is the set of paths that still connect to the rest. This way of drawing also cures a common fear of infinity. Because conformal maps keep angles, not lengths, they pull infinite distances into finite lines while preserving who can reach whom. A line marked spatial infinity is not a cliff. It is a reminder that you could travel forever in that direction without meeting a border. A black hole horizon, drawn as a straight line, is not a shell of matter. It is the place where outward-aimed light turns inward. These diagrams are not photographs of the universe. They are scores for the symphony of space-time, keeping the light ray skeleton intact so we can see structure at a glance. With practice, they answer hard questions quickly. Is the space-time geodesically complete? Are there true singularities where paths end? Do horizons form, and if so, which regions become causally sealed? In classrooms and papers, they turn long equations into pictures the mind can hold. While conformal diagrams map causality, galaxy surveys map matter. Early astronomers expected a near uniform sprinkle of galaxies across the sky, with only mild clumping. What the surveys revealed was bolder, the cosmic web. On large scales, the universe looks like a network of filaments meeting at massive clusters with wide voids between them. Filaments are chains of galaxies and dark matter stretched over hundreds of millions of light years. At their crossings sit galaxy clusters, huge knots containing thousands of galaxies, hot X-ray gas, and deep dark matter wells. Between these bright junctions lie voids, vast, underdense regions that can span comparable sizes yet contain only a few small galaxies. Voids once tempted people to imagine cosmic walls or ends, places beyond which there was nothing. But a void is not a boundary. It is a low-traffic district. Step into one and you do not fall out of space. You just find fewer neighbors. A helpful picture is a foam. The thin walls are the filaments and sheets. The bubble interiors are the voids. The foam extends in every direction without a final panel where it stops. This pattern formed naturally. In the early universe, tiny differences in density, seeded by primordial fluctuations and recorded in the cosmic microwave background, grew under gravity. Slightly denser regions pulled in more matter and became filaments and clusters. Slightly emptier regions bled matter to their surroundings and became voids. Over billions of years, expansion stretched the grid while gravity sharpened the contrast, sculpting the web we chart today. The web looks intricate, yet it obeys a simple rule at the largest scales: homogeneity. Zoom out to hundreds of millions of light years, and the knots and gaps blend into a near-uniform haze. Like a forest seen from high altitude, the patchwork becomes a smooth field. This large-scale smoothness supports the cosmological principle, the idea that, averaged over enough volume, the universe looks statistically the same everywhere and from every vantage point. There is no special center, no great wall that marks an end, no privileged edge where structure ceases. Filaments and voids repeat in different arrangements, but their overall statistics match from region to region. Seeing both pictures at once, the causal map and the matter map clarifies where space stops. Causally, space is sliced by horizons. Past horizons set what we can see now. Future horizons set what we can ever influence. Those are ends of contact, not ends of existence. Structurally, space organizes into a web without a rim. Dense knots, long strands, wide basins, all nested within a large-scale average that is the same in every direction. As dark energy takes over, the causal windows shrink in practice, while the web within our reach freezes into a quieter pattern. Beyond our horizon, more web continues untouchable, but still part of the whole. De Sitter space, in this light, is not a sterile fantasy but a guide. It shows how an accelerating cosmos parcels infinity into finite views, giving each observer a permanent horizon while leaving the universe itself unbounded. Conformal diagrams make those horizons visible on a single page. Galaxy surveys fill in how matter has arranged itself within the part we can see. Together they replace walls and edges with limits and maps. The universe does not stop. Our lines of sight do. The night sky does not hide a border. It hides a horizon. And the great pattern of matter, while lacy and dramatic up close, smooths to a common average when you step back far enough, confirming that we live in no special place, in a cosmos with no outer fence, and with boundaries drawn only by the reach of light and time. Voids make it easy to imagine borders. If you live deep inside one, with only a few faint galaxies on your sky, you might decide the universe stops just beyond your reach. Travel far enough, though, and a filament would appear, then a cluster, then another wide, quiet region. The pattern repeats in new arrangements without hinting at a final wall. Survey maps can also fool the eye. Sharp edges in published plots often mark where observations end, not where space ends. The blank zones are footprints of instruments and time, the cartographic limits of a particular campaign, not a statement about nature. Beyond the map, structure continues. The cosmic web ties scales together. Dark matter forms the scaffold. Gas cools along that scaffold and gathers. Galaxies ignite where the lanes cross. Stars build within galaxies. Planets assemble around stars, and chemistry takes hold on some of those worlds. The empty reach of a void and the crowded weight of a cluster are two outcomes of the same growth. Gravity amplified small early differences, drawing matter into lines and nodes while leaving broad basins between them. The web is a texture, not a barrier. If you average over larger and larger volumes, the contrasts soften, homogeneity reasserts itself, and the sky becomes statistically even. Seen from a vantage outside the web, if such a vantage were possible, the pattern would look like softly lit strands and bright knots, with dark bays opening between them. come closer, and each knot resolves into thousands of galaxies moving in a deep shared potential. Closer still, and disks, star clusters, and clouds fill the frame. Pull back again and the speckled picture turns smooth. Large-scale structure sits between the bustle of local detail and the calm of the widest average. Talking about it means naming a scale, not marking a fence. A classic question addresses edges from another angle. Why is the night sky dark? If stars filled a static, eternal, uniform universe, every line of sight would end on a star's surface, and the sky would blaze like the sun. This is Olber's paradox. Dust cannot fix it, because in an eternal setting, the dust would heat and glow until it erased the darkness. The modern answer rests on three facts. The universe has a finite age, so only light that has had time to reach us since the hot beginning can contribute. Stars live finite lives, so not all possible sources shine at once. And space expands, stretching wavelengths and diluting energy before the light arrives, pushing much of the background into the infrared and microwave bands. Darkness follows from history and growth, not from nearby emptiness. The darkness is not empty of meaning. Between the stars, a faint microwave glow fills all directions, the remnant light from the early hot plasma. Your eyes cannot see it, but radio receivers can. That soft background, together with the dark, says the universe began, changed, and stretched. A black sky needs time and expansion, not a surrounding wall. Questions about total size bring the same logic back. The observable cosmos spans roughly 92 billion light-years across today, because that is how far light has reached us through expanding space. This number names a horizon, not the whole. We cannot look beyond it to check the rest. That one sky reality introduces cosmic variance. We have one realization to measure. As a result, statements about size are constraints rather than proofs. We can set lower limits. We cannot certify infinity by measurement alone. Curvature provides a strong constraint. Positive curvature implies a finite total volume. Flat or negative curvature allows an unbounded extent. Measurements of the cosmic microwave background and the distribution of galaxies indicate curvature consistent with zero to tight precision. If space is closed, its radius of curvature must be vast, so large that our patch looks flat. The statistics of the web support the same view. On scales of hundreds of millions of light-years and up, the pattern settles to uniformity, without hint of a nearby edge or preferred center. Inflation, a short, early burst of rapid expansion, explains why the universe looks so smooth and so nearly flat within our horizon. It also suggests the full stage exceeds our visible slice by a huge factor. Some models effectively produce an unbounded space. Others allow a finite but extremely large cosmos that could wrap on scales well beyond our sight. Inflation does not fix the total size by itself. It says our view is a small local patch. The rest depends on how long inflation lasted and on the physics that drove it. A finite yet unbounded universe remains a live option. In such a geometry, straight lines geodesics can close. Travel long enough and you return to your start, not because you looped around an object, but because space connects to itself. If the loop length were modest, light could circle, and we might see multiple images of the same distant galaxy from different directions and different times. Searches for matched circles in the microwave background and for repeated structures in galaxy surveys have not found clear signatures. That pushes any RAP scale outward. or leaves the possibility that the telltales are too subtle for current data. The concept stays clean, even without a detection. Closure without borders is a geometric property, not a demand for a physical rim. Voids are easier to read with that mindset. A deep void is a low-density district, not a seam in the fabric. A bright cluster is a crowded square, not a barricade. Survey edges mark where observing time ran out, not where space stops. As instruments improve and observing programs widen, maps fill, filaments extend, and voids link, and the same theme repeats. Structure continues, averages smooth, no wall appears. The night's dark canvas carries the same message in a different form. Without a beginning and expansion, the sky would not be dark. With a beginning and expansion, it stays dim. The microwave background plays the role of the bright surface moved out of sight by redshift. As time passes, that background slides to longer wavelengths and lower brightness. Dark energy adds another layer by setting a future event horizon. Beyond a certain distance, new signals emitted now will never arrive. Many galaxies that we can see today will cross that limit. They keep forming stars or fading on their own terms. What changes is our ability to share signals with them. Operational tools turn these ideas into tests. Standard candles like Type Ia supernovae trace the relation between redshift and distance and revealed the accelerating expansion. Standard rulers like the acoustic scale in the CMB and baryon acoustic oscillations, fix geometry. Weak gravitational lensing maps the hidden mass skeleton, tying light to the underlying dark matter. Redshift surveys fill three-dimensional volumes with millions of galaxies, testing homogeneity and searching for repeats. Gravitational wave detectors add timing marks and new messengers from mergers far across space. Each dataset shrinks the space of viable global shapes without pretending to see an outer fence. Language follows the measurements. Into what is the universe expanding? Into nothing, because into implies an outside the model does not include. Expansion is a change in the metric, not motion into a room. Where did the Big Bang happen? Everywhere, because every location was part of the hot early state. Is there a center? No. Any observer sees the same large-scale statistics when averaging over enough volume. Could space wrap? Yes. Current limits push any detectable wraps beyond our horizon. Keep two frames in view while reading any map. The structural frame is the web filaments, nodes, and basins grown from small early ripples and average to smoothness on the widest scales. The causal frame is the network of light cones and horizons past for what can reach us now, future for what we can ever influence. Together, they replace borders with limits and replace outside with beyond contact. The cosmic web is broad, but not bounded. The dark between stars is history, not a sign of offense. Total size is constrained from below, and closure without edges remains possible at scales we cannot yet probe. Now picture a wraparound cosmos in daily terms. In such a space, geodesics return. A traveler pointing straight could, in principle, come back from behind after crossing the loop length. Light could do the same. The sky might host subtle repetitions, distant structures seen at several stages of their lives, separated by angle and by time. Without a detection, navigation stays ordinary. With a detection, charts would include global routes. Either way, the idea shows how geometry can limit volume without inventing a wall. For a sleep-friendly thought experiment, imagine setting off along a straight path at steady speed. For long stretches, you pass voids and filaments, clusters wheeling slowly, then fresh quiet again. If space connects to itself on scales beyond our current horizon, that path would eventually take you back to a familiar neighborhood from a new angle. If space does not connect that way, the path would continue through new volumes without end. In both cases, what breaks the myth of the wall is the same pair of guides, the texture of the web and the reach of light. Picture traveling in a straight line for ages, never turning, never circling a star. One night, the sky ahead begins to look familiar. A pattern of bright points lines up just so. A shape you know clicks into place. You have come back to where you started, without looping around anything local. The circle you traced was not on a map of towns and roads. It was in the fabric of space itself. In a wraparound universe, straight paths can close. The sky could even contain quiet repeats constellations that are really the same far region, seen from a different direction and a different time. Astronomy in such a cosmos would ask careful questions. How do we tell a second view of the same galaxy from a new one that only looks similar? Matching shapes would not be enough, because galaxies age. Another check would be the ancient light of the cosmic microwave background. If space loops on scales, near a horizon, that afterglow should show repeated patterns, pairs of matched circles with the same tiny ripples. Surveys have searched for those signatures and not found them. The clean reading is that if space closes, it does so on scales larger than we can see today. Even so, the idea earns its keep. It shows that a universe can be finite yet free of walls. Geometry alone can make a world that is complete and still feels unending. The picture can be calming. A wraparound cosmos does not shrink the universe. It adds connection. It says, endless need not come from infinite size. It can come from the possibility of return. Whether or not space actually closes, the result for us is similar. The night keeps its mysteries. Some may be echoes, some will always lie beyond reach. Edges stay elusive, paths stay long, and the question, does space stop, keeps its honest answer, not in any way you can meet like a cliff. Infinity needs the same care. People often imagine an infinite universe as a flat sheet that never ends. Infinity, though, is not a place you can reach. It is a property. There is no last step. If space is infinite, you never arrive at the edge of infinity. You just keep going, and there is always more beyond. That picture can feel unsettling or soothing, depending on your mood. It removes the fear of a rim and replaces it with open, quiet continuation. A popular claim says that in an infinite universe, everything must repeat another Earth, another you, repeating every detail. That logic assumes the number of possible physical states is finite. If the menu of arrangements is finite and the space to place them in is infinite, repeats follow. But if the menu itself is unbounded, if physics allows endlessly many distinct states, then space could stretch forever without exact copies. Mathematics helps here. The whole numbers are infinite, yet no number repeats. Infinity means no end, not guaranteed duplication. In cosmology, when scientists speak of an infinite universe, they mean our best measurements do not force a finite boundary. The models allow unending extension. Whether nature actually uses infinity, and whether that would bring repetition, lies beyond what telescopes can decide. Even as a hypothesis, infinity sets a usable frame. It turns the dome of the night into a window with no back wall. It does not erase our place. it scales it. A single life still matters, the way a single note matters in a long piece of music. The length of the score does not cancel the note, it gives it context. Infinity also shows where science meets its limits. We cannot check all of space. No result will ever scan the whole and declare no edge anywhere. Infinity lives at the border of measurement and idea. That does not make it useless. It tells us how to read our data without forcing conclusions we cannot support. The multiverse sits in the same cautious zone. The word invites pictures of countless universes stacked side by side. In physics, it points to families of models that try to explain why our universe looks the way it does. One path begins with inflation, the brief, early burst of rapid expansion. In some versions, inflation ends only in patches. Where it ends, a hot bubble universe like ours forms. Where it continues, space keeps stretching. The process never finishes everywhere at once, so new bubbles keep appearing. Our observable world is one bubble interior. Beyond our horizon, other bubbles could exist, separated by regions that still inflate faster than any signal can cross. Another path comes from string theory. That framework admits a vast landscape of possible solutions, each with different values for physical quantities. If some mechanism like inflation can populate that landscape, the result is a multiverse rich in variety. In principle, different bubbles could have different physics, different particle masses, maybe even different numbers of large-scale dimensions. We would still see only our interior, because the separation between bubbles prevents contact. What would count as evidence? Direct sightings are out by definition. Indirect hints might exist. A collision between bubbles in the very early universe could have left a faint mark in the microwave background, a bruise-like pattern, or a circle of unusual temperature. People have looked. Nothing decisive has turned up. Another line is more philosophical. The constants of our physics look friendly to chemistry and life. In a multiverse with many bubbles and many constants, observers naturally find themselves in a bubble where conditions allow observers. That logic does not prove other bubbles. It undercuts the need to explain apparent fine-tuning with a unique mechanism. The honest status is simple. The multiverse grows from serious physics, but it remains speculative. It widens the stage of questions. It does not remove the need for evidence. None of this is needed to feel awe. One universe already gives us more than we can map. A web of filaments and clusters, a fossil light from the first atoms, a history that links tiny early ripples to today's galaxies. If other bubbles exist, they add to the wonder. If not, the wonder stands. Under all these ideas sits a working habit, measured uncertainty. Cosmology lives with limits in a precise way. We learn from signals, not from direct touch. Photons hit detectors, radio waves stir antennas, weak lensing gently skews galaxy shapes, gravitational waves ring through laser arms. Every step in that chain carries noise and bias that must be modeled and removed. Some limits are baked in. Cosmic variance is the classic example. We have exactly one sky. We cannot observe dozens of universes, average their microwave maps, and quote the mean. The pattern we see in the cosmic microwave background is one realization of a random process. That built-in scatter does not evaporate when instruments get better. It is part of the game. Other limits are practical. Telescopes have finite mirrors and finite time. Detectors have dark current and readout noise. Space observatories dodge air and weather, but they still warm and cool. and their electronics still whisper. At radio wavelengths, the Earth itself is loud. At optical wavelengths, the sky glows. At infrared wavelengths, everything warm is a source of background. Survey footprints have edges. Fiber positioners miss some targets. Bright stars mask faint neighbors. None of this ruins the picture. It shapes the error bars and the care to handle those limits. Cosmologists cross-check. Use standard candles. Type Ia supernovae to map brightness versus redshift. Use standard rulers, baryon acoustic oscillations, and the angle of the first acoustic peak in the microwave background to fix geometry. Use weak lensing to follow mass where light is scarce. Use galaxy clustering to trace the web in 3 dimensions. Use gravitational wave events as standard sirens to add independent distance measures. The goal is not a single perfect proof. It is a network of constraints that agree within uncertainties. When the lines cross in a tight region, confidence grows. When they do not, the mismatch becomes a clue. This attitude also keeps language honest. Edge becomes horizon. Beginning becomes past incompleteness, unless the data force more. Infinite becomes not bounded by current constraints. Evidence becomes signal above noise, with systematics tested. The change is not cosmetic. It is a way to keep ideas tied to measurements. Turn back to the open questions with that in mind. If space wraps, the loop scale lies beyond present reach, or the signatures are too subtle. Surveys keep pushing. If space is infinite, that remains a model choice consistent with data, not a measurement we can finish. If other bubbles exist, their marks, if any, are faint and not yet found. If dark energy is a pure constant, the far future trends toward a de Sitter-like calm. If it evolves, new physics waits. The path forward is methodical. Deepen maps, widen wavelength coverage, improve calibration, and let the combined constraints tell us how far the unseen stretches. None of this requires drama. It asks for patience and clear frames. Horizons sort what can connect. Geometry sets how distances behave. Noise and variance set how well we can know. Within those rules, a universe can be finite without a wall, infinite without repetition, or part of a larger process without changing anything we measure tomorrow. Stand under the night and let that steadiness do its work. If space one day turns out to loop, the sky will reveal it through echoes. If it does not, the sky will remain open with no rim to find. If there are other bubbles, their story will stay beyond contact while ours continues. What we can trace today is already remarkable. A fabric that expands, a web that grows, horizons that shift, and signals that carry a history long enough to fill a lifetime of curious listening. Astronomers spend much of their time removing flaws from the data before they can study the signal itself. The universe is generous in size, but stingy in information. What reaches us is a slow stream, always mixed with static. That is why you see error bars on plots and numbers. An error bar is not a failure. It is a clear statement of how tightly the result is pinned down. When you hear that the age of the universe is about 13.8 billion years, the value comes with a narrow range around it. That small band is not weakness. It shows that we can say where uncertainty begins. Another habit worth keeping is the difference between not seen and not real. In daily life, we often treat the absence of evidence as evidence of absence. In cosmology, the silence may simply mean the signal is too faint, the survey too short, or the clue lies just beyond our horizon. A quiet sky does not prove there is a wall. A lack of repeated patterns does not prove the whole is infinite. It reminds us we are still reaching. There is comfort in learning to live with that. The universe does not reveal everything at once. Knowledge arrives step by step, with limits we can describe. To demand a final answer is to miss how discovery works. The measured uncertainty is not a gap where anything goes. It is the frame around what is known. At a calm pace, that frame is soothing. Picture the cosmos as pages written in light. Some lines are sharp, others are faint. You can read enough to follow the story while leaving the missing sentences unfilled. Patience is part of the method. This habit of patience is why the field is resilient. New instruments sharpen the picture. New surveys widen it. Models are updated, not defended at all cost. The progress looks like sketching. Broad outlines first, then detail, with room for correction. The eraser matters as much as the pencil. Sometimes the uncertainty itself is the most useful part. Consider the current tension in the Hubble constant, the rate of cosmic expansion. One set of methods favors a slightly higher value, another favors a lower one. The mismatch might be systematics, still hiding in the data. It might also point to new physics. Either way, the disagreement is not noise to ignore. It is a sign where to look next. In this sense, limits are not walls, they are doorways. Cosmic variance tells us that one sky is all we get, and that some kinds of uncertainty will never go to zero. But it also tells us exactly how to draw the error bars. Instrument noise reminds us of imperfections and pushes engineers to design better detectors, colder optics, cleaner readout. Uncertainty is not vagueness. It is disciplined. It directs effort. You do not need to settle every question before sleep. The universe keeps many of them open, and that is all right. What we know is sturdy because it admits its limits. Error bars and confidence intervals are a form of honesty. As you think about the faint signals gathered by telescopes and receivers, keep this in mind. Precision is not perfection, and uncertainty is not ignorance. It is careful learning. Whether space ends is a question we may never answer, but the space between answers can hold quiet, and quiet can help. Metaphors help carry these ideas. We reach for balloons, bread dough, ripples, and spheres because pure equations are hard to picture. They are stepping stones across a deep river, but they can slip underfoot. The balloon image captures metric expansion, every point moving away from every other, without a center. Yet it tempts us to imagine an outside air the universe expands into. The raisin bread picture shows distances growing between raisins, but the loaf sits on a tray in a kitchen. The Big Bang is called a bang, but it was not an explosion into space. It was space itself expanding everywhere. At night, when the mind wants rest, two literal pictures can set traps. Into what is the universe expanding is a balloon question, not a physics one. Once you drop the outside room, the puzzle drops with it. Better images mislead less. Think of the surface of Earth. Walk far enough in one direction, and you never meet an edge, yet the surface is finite. Or think about slow ripples on a pond, not as things thrown into water, but as the water's shape changing in place. No picture is perfect, but some carry less baggage. Even better than new metaphors are better questions. Not where does space stop, but how far can signals reach? The first invites walls, the second invites horizons, which we can define and measure. Not what is space expanding into, but how does the scale of distance change with time? That leads to the metric and to redshift. Not what is the center, but what geometry and topology fit the data. That leads to curvature, to tests with ancient light, and to the search for repeating patterns. This shift does not shrink wonder, it deepens it. Asking for a wall sets you up for an answer that nature likely does not give. Asking about horizons, geometry, and topology opens paths where instruments and math can meet. The wonder becomes steadier, a web that continues without a rim, a near flat space that could be infinite or very large, a light background that carries the imprint of early sound waves, a future horizon set by dark energy that turns some galaxies into permanent silences. Language itself reminds us to be gentle. Dark energy is a label, not a description. It is not literally dark, and energy is used in a specialized way. Cosmic web is an image, not a net of threads. These names help us talk. They do not fix the reality. Hold them lightly. The best terms are the ones that hint at their own limits. Pull the lessons together, and the picture is steady. Space is not a box with walls or a stage you can walk off. It is a fabric defined by distances and durations, by the paths of light and the paths of matter. Gravity shapes that fabric. Expansion stretches it. Causality stitches it into regions that can share signals and regions that cannot. When we ask where it stops, we are really asking where our contact ends. Horizons make that answer precise. Your past light cone gathers every event that could have reached you by now. Your future light cone contains every place your signals can ever go. The observable universe is the slice of reality that has stepped into our past light cone since the hot early phase. Nothing special happens at its edge in space. The change is in time. Farther out, with dark energy in control, a future horizon slowly divides the sky into parts that can still talk and parts that never will again. The galaxies beyond do not vanish. They fall out of conversation. Geometry gives this quiet a shape. Positive curvature can make a space finite, yet without borders. Zero or negative curvature can allow an unbounded extent. None of these cases requires a rim. The rules tell you how lines and angles behave, how straight paths travel, whether triangles add up to exactly 180 degrees, or a little more or less. Topology asks whether space links back on itself. It allows closure without edges for straight paths to return, while the lack of obvious repeats so far says only that such closures, if real, lie beyond our current reach. The oldest light on the sky, the cosmic microwave background, makes these ideas tangible. Its slight temperature ripples record early density waves and carry clues about curvature and possible global wraps. We read those ripples with care. They tell us our patch is nearly flat and very uniform. They tell us that if there is looping on a grand scale, it is larger than our horizon. Inflation explains the smoothness, sets the stage we can see, and plants the seeds that grew into galaxies. Dark energy later adds a gentle acceleration that fixes a future limit on contact. None of these pieces force an edge. Together they replace edges with rules. Across all of this runs the theme of measured uncertainty. Our view is one view. Instruments have noise. Sky coverage has gaps. Cosmic variance sets a floor. We write down those limits and keep going. Absence of evidence, no matched circles, no repeating skies, does not compel a strong claim in the other direction. It invites longer looks, deeper maps, and better tests. So the working answer remains calm. Space likely has no hard edge. What ends is our reach. The limit moves as time passes. Sometimes more of the sky steps into view. Sometimes expansion pushes parts of it away for good. The rules are steady, even when the picture changes slowly. A fixed speed for signals, a metric that evolves, gravity that curves paths, and a web that grows where matter gathers. Hold one last picture as you drift toward rest. Imagine yourself under a quiet sky. From where you are, a sphere of influence grows at the speed of light. Everything already inside has had time to speak. Everything just beyond may speak later. Farther still are places that will never send a new message because the current carries them outward too fast. The sphere expands. It never meets a wall. It meets only the bounds set by time and by how space itself behaves. Beyond that line, the dark is patient, not empty, just waiting, or forever out of reach.